Yeah, okay. We'll continue our discussion about ANCOVA, MMRM, and Estimand. So I hope the last session will give you a very clear understanding what an ANCOVA model, let me put it this way, in a pre-specified manner. So at the design stage, you want to pre-specify your analysis model, and ANCOVA has been widely accepted. And today we're going to get into MMRM, and then we're going to get into some other varieties of MMRM, and we'll talk about Estimand. ICH-E9, of course, International Conference on Harmonization, E9 is statistical principles, and they talk about intention to treat. This is fundamental. Intention to treat is very critical from the alpha protection point of view. And so we need to pre-specify the primary analytical model at the design stage. Analysis has to respect design. So we want to be sure that everything is clearly pre-specified so that the alpha can be fully protected. So intention to treat has two fundamental principles: report all data, analyze as randomized. So for clinical trial, sponsors need to report all data to regulatory agencies. That we will understand. But the question is that all data means all patients or all visits. The interpretation is different between the physician and the statistician. And that is why there are many different ways of understanding how to analyze the data, how to, from medical point of view, from statistical point of view, how to submit an NDA, how to approve a drug or stuff like that. So we'll get into some more details about this. The key of these two different views came from the profession. The medical profession are trained to look at the patient as a complete person. So there's a person in front of this physician. The physician will have to make the best diagnosis based on the understanding, the knowledge from test results, whatever. They have to make the best diagnosis for this patient. And based on the best diagnosis, they're going to select the treatment for this patient. So from a medical point of view, when they look at report all data, they say every patient needs to be reported. The training of statisticians are different. Statisticians are trained to think of data came from a population, and we're taking a sample from the population, and we want to study this sample. After the study from the sample, we'll try to make inferences back to the population. So from the statistical point of view, the quote-unquote population is being defined by the user. If the user is a statistician, this user will say, well, I'll define report all data being report all visits. And a statistician could also say every patient should be analyzed as equal weight, one patient, one vote. So it really depends on the user how to define this population. And that's different thinking from physician, because physicians in medical school and everything, they're training, they're looking at every patient as a whole person. So when you sort of discuss or understand or communicate the way of thinking between statistician and the physician, this interpretation will be different. All right. So every patient counts. So one patient, one vote. But from a statistical point of view, well, if I define the population being all the visits, now multiple visits from the same patient are correlated. So that's a fundamental difference between the view of all patients and all visits. And that triggers the way of thinking about missing data. So if you report all patients, then every patient participating in the trial is an individual patient. There's no missing data. These patients are in the study from a medical point of view. But from a statistical point of view, if you look at longitudinal clinical trials, patient dropout, missing data are common. They saw these visits are missing. Many statistical literatures deal with missing data. That's from a statistical point of view. But from a medical point of view, the patients are there. The patient is not missing. The visits are missing. So the difficulty of this different recognition creates a lot of communication gaps. But for a drug approval, there has to be at least 3 sets of communications. All right. The first set of communication happens within the company when they design the trial, when they analyze the trial, is the discussion between the physician and the statistician, try to communicate and understand what they try to do. Only after they come up with a mutual agreement and then they file an NDA. Now the NDA goes to regular agencies. Within the regular agency, there's another communication between the physician and statistician. By looking at this NDA, whether they can approve the drug or not. And so there is this close communication between physicians and statisticians in the regular agency. And the third level of communication is the communication between the company and FDA. So there are all sorts of communication happen, trying to understand whether the drug should be approvable or not. And the understanding of missing data plays a major role in these discussions. So when we talk about missing data or missing visits, patient dropout, this is just a simulated data set to say, now patient number 1 dropped out at visit 6. So this study is a 10-visit study. Now the next patient dropped out at visit 5 after visit 5, and this patient completed the study, and so on and so forth. So how do we deal with these? A statistician look at this data and say, there's a lot of missing data here. But the physician look at these data to say, every patient is there. It's just different patient stay in the study for different lengths. So that's the major difference between the medical point of view and the statistical point of view. So suppose this is a complete data set. Now, what if this patient drop out after visit 2? Let's see what happened. So the patient drop out after visit 2. Now, there's a term they call LOCF. I don't think this is a correct way to call it. It really should be a last observation analysis. There's nothing, it has nothing to do with carry forward. Let me try to be clear in the later discussion. All right. Now, the patient drop out after visit 2. All right. Let's go back to the intention to treat principle. Intention to treat, if we want to analyze every patient, and the study is designed that the primary endpoint happened at visit 5. All right, that's the design. The design says we're going to analyze at visit 5. Now, this patient dropped out. So this patient does not contribute to visit 5. So a physician would say, okay, every patient is equally important, right? For these 3 patients who have visit 5, that's fine. For this patient, why don't we just analyze the last observation? Keep in mind, it has nothing to do with carry forward. It's the analysis of last observation. All right. Now, that understanding sort of differentiates between the medical point of view and statistical point of view, because medical point of view says every patient should be weighted equally. 1 patient, 1 vote. So this patient contributes this piece of data. These 3 patients contribute their data here. The statisticians interpret this thing differently. They say, what if we consider this as visit 5? And now we we can analyze of visit 5 data. So the statistician called it last observation carried forward. Well, that misunderstanding creates the next confusion, right? Now, if you consider it as carrying forward, you're assuming the patient's reaction or response at this point, and at this point are the same at this point. And so the statistician called it imputation. That's a misunderstanding. There's no imputation here. It's just analyze the last observation. But the statistician would say, well, we're focusing on visit 5, and visit 5 is missing. We're considering this as visit 5, we're carrying forward to visit 5. But in fact, that was not the case. The analysis is last observation only. There's no carry forward, just analysis of last observation. Now, if you consider it's an imputation, then the statistician could claim, well, there should be some variability here. Well, from here to here, there should be a variability. There should be a variability. There should be a variability. But by imputing, you are not considering the variability. And so they say LOCF underestimate variance. If you look at it from LOCF point of view. But the fact this is just the last observation analysis has nothing to do with carry forward. So between the physician and the statistician, they discuss and say, what if we look at another analysis? If patient does not have visit 5, we don't include them. So you just analyze these 3 patients. All right, so this set of analysis, now, of course, we know it's violating the ITT principle. You're not reporting all data. But at least you're analyzing visit 5. So this analysis, people call it completer analysis, or they call it observed cases analysis, OC analysis, observed cases analysis. But people believe that this analysis is kind of biased. The computer analysis or observed cases analysis biased because for one thing, it's not reporting all data, and then for another thing is that this does not represent the entire patient population point of view. So that's a major confusion between statistician and physician. So computer analysis for subset analysis, complete the study, also known as observed cases analysis. If dropout rate is low, computer analysis should be close to the last observation analysis. But computer analysis violates ITT. So the academic statisticians began to criticize LOCF to say they're either overly conservative or anti-conservative, and to say it's best point estimate, and they claim it's underestimate variance. So we talk about a little bit about this underestimate variance. I think that claim of LOCF underestimate variance is a different interpretation than last observation analysis. All right. Now, in last observation analysis, it's 1 patient, 1 vote, and we're just performing the last observation analysis. There's no carry forward, so there's nothing to do. It has nothing to do with underestimate variance. If people claim it's underestimate variance, that is, you assume these data points are included in the analysis, then it could violate, it could cause the underestimate variance. But the last observation analysis did not include any of those data. They just include this data because it's 1 patient, 1 vote. And now, the academic statistician claimed that LOCF being a biased point estimate. Right, that's a statistical point of view. Because at the design stage, if you claim your primary analysis is based on visit 5, then of course, the visit 2 does not represent visit 5, so that's biased. But on the other hand, if we think about the purpose of drug development, the purpose of drug development is to help the patients and help the physician. So for a physician to make a prescription, what does a physician think? All right, so there's a patient in front of me, and I'll do my best try to understand the patient's history, from the lab tests or other diagnostic tests or whatever, and then even patient's family history stuff. I will try to understand the patient to the best of my ability, and then I'll make a diagnosis. Okay. Now, after making this diagnosis, then I will have to figure out the best treatment for this patient. Now, while I was thinking about the best treatment for this patient, I'm thinking of, when I made this diagnosis, I'm thinking of the other patients I have diagnosed before. And they received different treatments. And how did they respond? So from the physician's point of view, the thinking is, for these other patients I experienced, what was their last observation? So when the physician making the diagnosis and selecting the treatment, the physician was not thinking about visit 5. The physician thinking was last observation. So if we understand the purpose of drug development and drug approval is to help physicians to make their best decision, then the drug label should use last observation to educate the physician. And in that sense, the last observation is the only unbiased point estimate. Because your parameter of interest is last observation. Your parameter of interest is not visit 5. But statisticians think that when I design the protocol, I'm looking at visit 5 as my primary efficacy endpoint. But that's a design point of view. But the drug development and drug approval should serve the physician, should serve the patient. So the way to communicate is really to use the physician's language to communicate. And from the physician's point of view, the only unbiased estimate would be last observation. So next, let's look at whether it's overly conservative or anti-conservative. All right, let's look at this data set. Now, if I'm looking at pain reduction, now the test drug reduced more pain than placebo. Okay, now at visit 7, placebo patient drop out. So we carry forward. All right, now you perform the analysis. The test drug patient at visit 10 has this value. Now you look at visit 7. So the treatment difference of last observation is greater than the treatment difference of visit 10. So in this setting, the last observation was anti-conservative. On the other hand, if we look at visual acuity, we look at the number of letters the patient could read. Now, the placebo patient deteriorated more than the test drug patient. Now, if at visit 7, the placebo patients drop out, and you're looking at the last observation analysis, you look at this difference compared to the visit 10 difference. Well, last observation analysis is conservative. So whether LOCF is conservative or anti-conservative, it has nothing to do with LOCF itself. It's really based on the setting. All right. So the criticism from the academic statistician about being overly conservative, anti-conservative, it has nothing to do with reality. And when the academic statistician claim LOCF being a best estimate, that's an academic point of view. That's not a practical physician point of view. All right. And the academic statistician claim that the LOCF is underestimating variability, and that's because they're not engaged in clinical trial. So for a 5-week trial, primary time point is week 5. And then LOCF is biased if your primary time point is week 5. Drug label helps physicians prescribe. How does a physician prescribe? Medical thinking is last observation. So from label point of view, parameters is LOCF or last observation. That's the parameter of interest, which is the only unbiased estimator. And we mentioned about whether it's underestimating variance or not. Based on ITT, every patient should be analyzed. For a patient did not complete the study, is the week 5 use last observation. There's no underestimation of variance. If you impute all observations after dropout, underestimation may happen, but that's not what was done. All right, so because of this misunderstanding of last observation, there were a lot of debate over the past few decades. So I think the criticism of LOCF starting probably in the early 90s, late 80s, early 90s. And that was about the time when SAS came up with PROC mixed. So when PROC mixed was first available in late 80s or early 90s, it has a lot of bug in it. It's very easily, you fit in the data set, the data doesn't converge, and you don't know what happened. But in the early to mid 90s, SAS did a lot of effort to improve PROC mix. So by late 90s, the PROC mix is pretty stable. So at that point in time, there's this understanding of MMRM. So I mean, academic statisticians were not happy with the LOCF. Now, so instead of LOCF, what else can you use? So they came up with MMRM. And then, of course, in early 2000, there are NDAs filing with MMRM as a primary analysis model. So what is MMRM? All right, this is the basic model of MMRM. All right, so I will talk about the brief history a little later, but let me just give you the history of what happened about MMRM. I think the first few NDAs in MMRM are early 2000. And if you look at those approval, all right, if you look at the approval is, say, even though the submission was MMRM, but the approval was based on last observation, all right. So then the many industry statisticians think that we should use MMRM instead of LOCF. And so they were trying to push FDA to accept MMRM. So in the mid, I think about 2003, 4, 5, 2006, 2007, around those years, there's a pharmaceutical work group, all right? So we know in US, there's a pharmaceutical pharma research and manufacturing association, PHRMA, Pharmaceutical Research and Manufacturing Association. So there's this pharma, within pharma group, there are different study groups. And of course, there's statistical study group, and the statistical group, there's a group study missing data problems. And so this group of statisticians, they published a paper in 2008. That paper was published in Drug Information Journal to say it's a pharma position that we should use MMRM. So I want to introduce this background because MMRM is a very specific form. So if you're deviating from this form, it's not MMRM, right? So in this specific form, Of course, this is part of a general linear model. Right? It's a general linear model where there's fixed effects, there's random effects. Right? That's how you understand this model. All right. Now we know that in talking about ANCOVA model in the previous lecture, the ANCOVA model were analyzing sort of one patient, one vote. Each patient contributes one piece of data. But the MMRM is different. MMRM, they're looking at one visit, one vote. So in other words, every visit is contributed to this analysis. So how do they contribute? So now your Y is no longer a single observation. It's not a scalar now. Y is a vector. So let's say there are 4 visits, right? So there's baseline, visit 1, visit 2, visit 3, visit 4. So Y sub I being the X patients change from baseline values. So they're change from baseline to visit 1, change from baseline to visit 2, change from baseline to visit 3, change from baseline to visit 4. All these 4 values became a vector. So this Y sub I is a vector. It's a 4x1 vector. All right, now this vector is expressed in terms of fixed effects, random effects, and residual. All right, so alpha is a common vector of fixed effects, and xi is a design matrix relating to observations of the I subject to alpha to these parameters. And bi is a common vector of random effects, and zi is a design matrix associated with the random effect. All right. So if alpha, say, if there are 10 parameters in alpha, for example, then X would be a 4x10 matrix. All right. So 4x10 multiplied by 10x1, that became a 4x1. All right. Now, so similar setting was Zi Bi. This is a matrix, this is a vector, and this is a vector. E1, E2, E3, E4 are the residuals associated to visit 1, visit 2, visit 3, visit 4 of patient number I or subject I. All right, so that is the common vector of random errors. And the MMRM paper from the 2008 that claimed this is appropriate under missing complete at random and missing at random. Now let's take a look at it. The fixed effect can be expressed by using the expected value. All right, so you look at the first moment. The first moment you take expected value of the this patient, the expected value of this patient I for all the 4 visits. That's X alpha, because once you take expected value, the variability or the variance just drop out. The random effects drop out. All right, so that's all you have. Now, if you look at the variance of Y, now the variance of Y, there's 2 components. There's ZIBI, which is the variability of this patient across visits. All right, so different visit has different variabilities. It's reflected from this part. And residual is the visit to visit differences. All right, so these are the within patient across observation variability, and this is a within visit variability. So there's these 2 components. All right, so within visit, across visit for the same patient. So that's the 2 variance components. And we assume that these 2 vectors, Bi and Zei, are independent. If you assume they're independent, then you have 2 variance components. You just sum them up. So this one being Zig, Zi prime, and this being residual. So let me give you a very simple way of understanding these 2 variance covariance matrices. Now, if you define identity matrix I, all right, identity matrix I have 4 visits. So this matrix is a square matrix 4 by 4. I have all the diagonal values being 1, off diagonal values being 0. So the 16 elements, there are 4 ones and 12 zeros. 6 0 on the lower triangle, 6 0 on the upper triangle. So that's identity matrix, that's I. Let's define a different matrix. Let's call it J, capital J. J is, again, a 4 by 4 matrix with all ones in it. So the simplest structure of this guy would be sigma 1 squared times J plus sigma 2 squared times I, right? So that's make it, everything is with the same correlation, same correlability kind of stuff. So you got the sigma 1 squared times a J matrix plus sigma 2 squared times an I matrix. So that's the random effect part of this model. So this is a very specific form of general linear model. This form is so they just call it mixed model, mixed effect models, repeated measures, MMRM. Mixed model with repeated measures. So this is specific implementation for clinical trial application. Now, for the so we call this model being the pharma recommendation. This being the pharma recommendation. The analysis is mean change from baseline. In other words, that vector y has visit 1, visit 2, visit 3, visit 4 of change from that visit, from baseline to that visit. All right, so your yi1, yi2, yi3, yi4 are changing from baseline. And fixed effect treatment. So we know treatment has to be in there. So we look at the fixed effect. So here we look at the random effect. Random effects, there are 2 variance components. That's how you handle it. Now you look at fixed effects. Fixed effects, there are the change from baseline, and the y is change from baseline. The fixed effect being treatment, tau I, right? And fixed effect of investigator side. So that's just like ANCOVA. In ANCOVA, we look at, instead of calling investigator side, you can call it the stratification factor. So any stratification factor you include in the model, you can stratification factor you apply in your trial, you can include in the model. Now this is a new thing, fixed categorical effect visit. So if I have visit 1, visit 2, visit 4, if it so happen becomes week 1, week 2, week 3, week 4, well, you can look at it as categorical effect, right? You have 4 visits. Or you can look at it as visit 1 being day 7, visit 2 being day 14, visit 3 being day 21, visit 4 being day 28. So if that's the case, you can look at it as a continuous effect, right? And then you can look at the day of the actual visit for this patient. Well, the actual visit may not happen on day 7, could be day 6 or day 8 or something like that. And so you can make that visit effect as a continuous effect. But here, the pharma recommendation is to treat it as categorical effect. And the next thing is interesting, treatment by visit interaction. When we talk about ANCOVA, I did specifically say that treatment by factor interaction should not be in the model, because from the design point of view, you do not include the treatment by factor interaction. But what happened to this treatment by visit interaction? What does it mean? Okay. Imagine if this pharma recommendation, there's no treatment by visit interaction, then what you're assuming is the treatment and visit, the difference are the same. The treatment difference, so the treatment difference are the same across visit. So you can think of a picture that there are 4 visits and you have test drug and placebo of 2 treatment groups. So at visit 1, the test drug and placebo, there's a difference. All right, at visit 1, there's a difference. And at visit 2, there's the same difference. Visit 3, the same difference. Visit 4, the same difference. So if you do not include treatment by visit interaction, you're assuming that the treatment difference between test drug and placebo at each visit is the same. They can both be high, they can both be low, but the difference is the same if you do not have that treatment by visit interaction. And we know by doing that, the assumption was too strong. We're assuming that there's no difference in treatment benefit across visits. So you cannot make that assumption. So that's why you include the treatment by visit interaction. So let me say why you cannot make that assumption. All right, if I want to have a 4-visit study, let's say week 1, week 2, week 3, week 4, the reason we designed the study this way is because we assume that the treatment difference at week 1 was not strong enough. And so week 2 should be stronger. Week 3 should be even stronger. The strongest treatment benefit happens in week 4. So the very simple-minded way to look at it is that if we're looking at reducing blood pressure, and we would assume the placebo has no effect. So your visit 1, visit 2, visit 3, visit 4, if you look at the difference from baseline, from each visit to baseline, then you can assume that there's 0, 0, 0, 0. All right, so the 4 visits of the placebo treatment group, their change in blood pressure at all 4 visits are the same. But then you look at the test drug, you want the test drug probably be lowering maybe 2.5 milliliter mercury at every visit. So in other words, at visit 1, the treatment difference between test drug and placebo could be minus 2.5. At visit 2, it probably become minus 5. At visit 3, it could be minus 7.5. At visit 4, it become minus 10. So you can see that over time, the treatment benefit increases. So assuming parallelism is not appropriate. So you really want to have the test drug will give you the best separation at visit 4. So that's why it is important to include this treatment by visit interaction in the model, in MMRM. And then fixed correlate baseline, we talk about baseline in the ANCOVA, so this carries the same meaning for baseline. All right. Now, baseline by visit interaction, so what does this mean? All right. Remember, when we look at the ANCOVA model, we look at baseline versus change from baseline. All right. So we have that graph where as baseline increases, your change decreases. So you have that scatter plot. Well, imagine that scatter plot reflects the change from baseline to visit 1. And then there should be a similar relationship of baseline to change from a baseline versus change from baseline to visit 2. Another graph for baseline versus change from baseline to visit 3, and another one for change to from baseline to visit 4. If you don't have this baseline by visit interaction, you're assuming all these 4 graphs, the slopes are the same. And that's too strong an assumption. So in order to allow the slope to change from visit to visit, you introduce this baseline by visit interaction. So this is the pharma recommendation, all right? So this paper was published in 2008. And then in 2009, there's another article from FDA, was published in Journal of Biopharmaceutical Statistics. So FDA says, okay, MMRM can be accepted for NDA. So after the 2009 paper, most of the pharmaceutical industry started submitting NDA using MMRM instead of last observation. So this is a variety of the model. So this is a random slope model that is assuming each patient or each subject has this individual intercept and slope. So this will be a kind of a different form of a repeated measure analysis. All right, for this repeated measure analysis, they're considering each patient contribute one intercept and one slope estimate. So this is time. All right, so this is the I think the ICE subject of GS treatment group at case visit. So again, you can look at it as a vector, but this vector you can reduce into a the 4 observations represented by k equal to 1, k equal to 2, k equal to 3, k equal to 4. So these are the time points. All right, so now you're looking at the visit as a continuous variable. You're no longer looking at visit as a categorical variable. So as a continuous variable, this could be the number of days post baseline. All right, and then of course this is a residual. So each patient is going to have his or her own regression line. And the random slope model saying that the intercept and slope, that each patient or each subject has his or her own intercept and slope. And then for the whole treatment group, within the treatment group, you're going to have a mean slope. You're going to have a mean intercept. So that's a different way of looking at the repeated measure analysis model. Again, this is also part of this general linear model or general linear mixed effects model. All right. So this model actually used in real world applications. In NDAs, there were NDAs using this as a primary analysis model. This can be thought of as a 2-stage process. The first stage is within patient regression. So each patient, you can calculate the intercept and slope. Individual, you're going to get individual intercept and slope. And now you can say Yj be the vector of observations of patient I in treatment J. All right, subject I in treatment J. So you can express that as a vector. So you can sort of y sub ij1, ij2, ij3. Now you make it a vector. Okay. In vectors. So now that vector is this one, which is these parameters and error ij, right? That's a vector. So that's the first stage. In the second stage, tau I represent the population intercept and population slope of treatment group J. So now beta ij equal to tau j plus bij. So now this is the second layer of this model. All right. So this one, you express this vector. You express this vector as a treatment plus an individual difference from the treatment mean. Okay. So now you have this model. So the response factor is now can be expressed as this, right? And the expected value is, of y sub ij of that vector become this. That's your expected value, and the variance being like this. And again, you have 2 components of random effects. Okay. So, like I said, I want to introduce this brief history of the evolution from LOCF to MMRM to Estimand. All right. So the 1962 Kefauver-Harris FDA amendment get FDA to start reviewing drugs with clinical evidence, clinical efficacy, and clinical safety. And of course, the early drug approval happens in 1970s. And the first wave of drugs approved are based mostly for hypertensive and to treat high blood pressure and for pain relief. And most drugs were approved based on last observations. And then they use computer analysis as a supportive analysis. So this was probably starting the 70s, the 80s, and the 90s, even the early 2000s, the drug approval are based on this concept. All right, your primary analysis being last observation, and then you have computer analysis and supportive analysis, and then if both your last observation analysis shows significance and computer analysis shows significance, then you think maybe the truth could be somewhere lying in between the last observation and the computer, and then they can be approved. So most of the drugs are approved based on that. So ProgMix was available in the 80s and beginning in the 1990s. Many people criticized LOCF. And ideas of MMRM became popular around the turning of the century. And then there's 2008 Pharma position paper. In 2009, FDA accepts MMRM. Before 2008, most drugs with primary endpoints as longitudinal continuous data were approved using LOCF. After 2009, submissions are mostly on MMRM and using LOCF as a sensitivity analysis. And then regulatory agencies started receiving MMRM. So after 2009, the review was mostly based on MMRM. Getting into 2013, many concerns raised about MMRM. I want to talk about communication. There are at least three sets of communication. The communication within the company, the communication with the FDA, and then the communication between the company and FDA. Now, if you submit MMRM, the physician started questioning, well, what are we trying to estimate? Well, the statistician will say, well, we're trying to estimate visit 5. Okay, what if visit 5 is missing? And the statistician say, now we have MMRM, we're incorporating all the data into the analysis. And then the physician says, do we still have one patient, one vote? Of course, there's no longer one patient, one vote. Now you're incorporating every visit into the analysis. So that comes back to the fundamental misunderstanding about intention to treat. Or you report all patients, or you report all visits. So from the statistician point of view, you're reporting all visits. But from a medical point of view, you're reporting all patients. And one patient, one vote. Every patient should share the same weight as the other patient. Now there's another problem underlying this discussion. Remember, we're talking about MMRM. There is this treatment by visit interaction. All right. So we know we had to introduce this term in the model, otherwise the assumption is too strong. But now by introducing this term in the model, your point estimate actually at the visit 5 is you're introducing this treatment effect, and you're introducing this visit effect. Now, if there is no treatment by visit interaction, then the treatment difference is averaged across all visits, which we should not do that because we anticipate later visits will give us better treatment efficacy. And the difference between test drug and placebo should be stronger than earlier visits. So that's why incorporating this treatment by visit interaction. But once you introduce this additional term, then your point estimate at visit 5 is more based on those patients who did have visit 5. So in other words, for the patients who did not have visit 5, their contribution to this treatment by visit interaction is weaker. That's why you no longer have one patient, one vote. So for certain missing data pattern, for certain situations, if their dropout rate is higher, now your visit 5 point estimate is more similar to a completer analysis. It's less similar to a last observation analysis. So which one should we believe? So that motivates the 2017 draft guidance about Estimand. They call it ICH E9R1. So in E9R1, what they try to do is this, all right? E9R1 try to bring the three things together, the analysis set, right? What is your analysis set? Intention to treat, complete, or whatever. What's your efficacy endpoint? What are you trying to estimate? What's your analysis set? What's your efficacy endpoints? And also, what kind of sensitivity analysis you want to perform. So they try to put all these things together in one thing called Estimand. And then for patient dropout or for patient took other medications, they call it intercurrent events. And they provide 5 strategies. So broadly speaking, there are only 2 major types of intercurrent events. Either it's missing data or patient dropout, right? So that's one type, one big category of intercurrent events. And another type being patients added other interventions. Could be background medication, could be rescue medication, or could be crossover to other treatment group. So in other words, when those events happened, the data is still there, but medically speaking, you cannot use those data because patients are adding drugs and things like that. All right. So missing data or intercurrent events are only these 2 types. One is missing data. The data is not there. For patient dropout, the data is not there. The other is that the data is there, but you cannot be used. And let's look at these 5 strategies under Estimand. The treatment policy strategy is fundamentally the traditional way of last observation analysis. All right. So, I'm sorry, I have to take that back. That was a well-on-treatment strategy. That was the last one. All right. The treatment policy strategy was something we used to call it retrieve dropout. So in other words, while we're doing LOCF, there were study designs that we say, well, what if patient drop out early? Then in the protocol, you specify, no matter when you drop out, at the last visit, you still bring the patient back. All right. So that's what we call retrieve dropout. So now the treatment policy strategy is the retrieve dropout way of data analysis. Well, composite strategy is sort of a good example would be a cardiovascular trial. A cardiovascular trial, you look at major cardiovascular events. What are major cardiovascular events? You're looking at stroke, MI, hospitalization because of cardiovascular events, or death because of cardiovascular events. Okay, so now if you have any of this event happen, now you claim the patient has an event. If during the whole study the patient did not experience any of the 4 cases, then you say the patient does not have the event. So that's kind of a composite strategy. Now there's hypothetical strategy. Hypothetical strategy was specifically designed for these model approaches like MMRM or random slope model, therefore the hypothetical strategy, all right? And principal stratum strategy is basically the completer analysis. You look at the patients who complete the study or the observed cases analysis. You look at patients who complete the study, that's the principal stratum, okay? And the while on treatment strategy, it was a traditional kind of LOCF analysis. So if you look at the fundamental spirit of this ICH E9R1, they're trying to do a couple of things. The first thing is that they want to use this document to improve communication between statisticians and physicians. I think that's absolutely critical. So when we read ICH in IR1, we should keep this in mind. How do we improve the communication between statisticians and physicians? And that's actually very helpful in designing a study, in interpreting the results and all that. Communication is absolutely critical. That's one thing, right? Another thing, the way I understand ICH in IR1 is they try to be inclusive. So in other words, they're not trying to say any way of analysis, you have to do just a particular way of analysis. So for any protocol, any trial, if you propose these one or two of these analyses as one being primary, the other being secondary, or something like that, they are all acceptable. So it's trying to be inclusive. So the objective is not trying to restrict to a certain type of analysis, but any type of analysis, if you can have a clear understanding between the physicians and statisticians, and also between regulatory agencies and the companies, then that's acceptable. All right, so that's the way I understand ICH in IR1. All right. So MMRM, because, okay, I want to come back, because the modeling strategy, all right, if you look at these other four strategies, the treatment policy strategy, composite strategy, principal stratum strategy, well, treatment strategy, they all respect this one patient, one vote. All right, this fundamental principle from the physician's understanding, one patient, one vote. All these four strategies, they satisfy one patient, one vote. But what if there's not one patient, one vote? Then you allow hypothetical strategy, different modeling approach. So I think I want to stop here.